Okay, Assalamualaikum warahmatullahi wabarakatuh and hello everybody. Okay, kali ini kita nak discuss tentang topik 7, Simple Harmonic Motion and Wave. Subtopik yang kita akan bincangkan pada video kali ini adalah 7.1 Kinematics of Simple Harmonic Motion SHM, 7.2 Graph of Simple Harmonic Motion, and 7.3 Period of Simple Harmonic Motion. In the subtopic 7.1 Kinematics of Simple Harmonic Motion, we will explain the simple harmonic motion and use the equation velocity, acceleration, kinetic energy and potential energy. Also, we will emphasize the relationship between total SHM energy and amplitude. In the subtopic 7.2, kita akan discuss tentang graph, which is we will analyze the graph for displacement time, velocity time, acceleration time and energy displacement graph. Untuk subtopik 7.3 Period of Simple Harmonic Motion, we will discuss the using of the expression for period of SHM, T for simple pendulum and mass spring system. So what is simple harmonic motion definition? Simple harmonic motion is a periodic motion. Periodic motion adalah back and forth motion about equilibrium position without losing energy. Okay, let's say we do have an object that is moving back and forth like that. Okay, so let's say the distance between one end to another end is 10 centimeter, and its center from one end to another end is 5 centimeter. So the center we call as the equilibrium position. So the simple harmonic motion keyword is we do have a periodic motion without losing energy. Next, this is the video representing the simple harmonic motion. As you can see here, the pendulum is same as the moving of the ball in circular motion. So some of the equation, we will use the relationship between simple harmonic motion and circular motion because it looks like the same. Right, in this video, I will show you the pendulum ball. As it moving, going up and down, and then we do have a ball that it rotate in a circular motion. So you can see here, it just the same thing. Okay, satu circle, satu putaran, okay, sama dengan one of the wavelength, which is equals to the distance ataupun the motion of the object of the pendulum naik dan turun tadi. So here is the slow motion. Okay, so you can see here the motion of the pendulum and the ball in circular motion. So jadi sama. So that's why in some cases pendulum bob is same as circular motion. Okay, this is the position of the amplitude of the pendulum. Then the ball in the circular motion is going back in 180 degree. So it means that in its equilibrium position, where the displacement is 0, and then it's going down, so we do have the negative amplitude. Okay, what's next? The pendulum bob, we're going up. Right, so it's already achieved the equilibrium position. So as you can see from the previous animation, the displacement is given by equation A sin omega t. Okay, kita ada graph sin. So the equation will be A sin omega t. The A represent the amplitude, the maximum displacement. Okay, so yang puncak ni adalah amplitude. And then sin omega t because we do have a graph sin. Okay, pattern graph dia, pattern graph sin. Okay, remember that to put your calculator in the mode of radian. Okay, because we do have omega, angular frequency here, which is in the unit of radian per second. So means that your calculator must be in mode radian. We also have equation of velocity or graph velocity against time, okay, where it's given by equation a omega cos omega t. As we know from previous lesson that the velocity is given by rate of change of displacement. So means that from this equation, from displacement equation, you differentiate, then you get a omega cos omega t. So that's why we do have graph like this. And then the next one is the graph of acceleration against time, which is given by equation a equals to negative a omega square sin omega t. From previous lesson juga, kita dah tahu, kita ada prior knowledge that the acceleration is equals to rate of change of velocity. So we do have here velocity, okay, differentiate by time. So differentiate this one, so we get negative a omega square sin omega t. What is means by the peak of each graph? So here we do have displacement in the y-axis. So maximum displacement we call as an amplitude, and this one is amplitude positive, okay, here. And then the below one is the amplitude negative. For the graph velocity against time, the maximum here we call as the velocity maximum. This one is negative velocity maximum. And then the last one for the graph acceleration against time, at the peak here we call as the acceleration maximum. The below one we call as the negative acceleration maximum. You can notice here that when you do have an object at the amplitude, at the same time its velocity is 0, but its acceleration is maximum. When the object at the equilibrium position, your velocity is maximum, but the acceleration is 0. We do have another equation of v in terms of displacement y. This is equation v in terms of time t. And then another formula for acceleration in terms of time y, in terms of y. This is equation of acceleration in terms of time t. Okay, how to use that equation? So let's say that you want to find the velocity maximum. We know that velocity maximum at the position of equilibrium position. Okay, from graph, velocity is maximum. So let's say we take this point, velocity maximum at the value of y equals to 0 at the equilibrium position. So we substitute in here. We choose this equation because we do have y. We can't use this equation because we don't have y. So we are using this, substitute y equal to 0. The next one, let's say the equation asks you to find the value of acceleration maximum. We know that acceleration maximum at the position y equals to amplitude. So A have amplitude means that maximum displacement. We are using this equation to calculate the acceleration maximum, not this one. Okay, back to the situation when we do have a spring that oscillate up and down. So what happened here? We do have elastic potential energy, which is given by half kx squared. But in this case, as we change to the physical quantity y, okay, which is displacement. Okay, kita guna y dalam this chapter. Okay, so the elastic potential energy is maximum, okay, bila kita fully stretch dia. Okay, so means that at the end of the oscillation, okay, paling hujung sekali dia punya stretching is maximum, right? So kita ada elastic potential energy maximum here and here, but it will minimum in equilibrium position. As it moving, so kita ada kinetic energy which is given by half mv square. So the kinetic energy is minimum at the end of the spring. but it is maximum at the equilibrium position. So from there, we do have equation kinetic energy in terms of displacement and potential energy in terms of displacement. So jadi bila soalan tanya calculate the kinetic energy maximum, okay, kinetic energy maximum at the equilibrium position means that y is equal to 0. So kita akan gantikan kosong dekat sini. Okay, this is the graph for energy versus displacement. As you can see here, the kinetic energy is increasing towards equilibrium position, but to the amplitude dia akan makin berkurang. Okay, but opposite with the elastic potential energy. Elastic potential energy is maximum at the maximum displacement, which is amplitude, but at the equilibrium position, elastic potential energy is 0. So same as in the opposite direction. So the total energy will be here. Okay, total energy is given by the summation of the potential energy plus with kinetic energy. So we add up these two equations, U and K. You will get equation of energy half m omega square A square. Okay, or we can write in terms of time T for U and K. Then the total energy will be half K A square. Right, K is a spring constant and then A is the amplitude. As an object oscillate, so we do have a restoring force, the force that will attract the object to the equilibrium position. So this force, restoring force, is always acted to the equilibrium position. We do have two cases. The first one is for spring and then the next one for pendulum. So the restoring force is equals to negative ky for spring. And then for pendulum, we do have negative mg sine theta. The net force is equals to ma. So when we make an equation, the A will be equals to negative ky over m for spring, and then A is equals to negative gy over L for pendulum. So we can see here, A and y in both cases is directly proportional. Means that when you push or stretch a spring or a pendulum, okay, kita tarik pendulum towards to the end ataupun to the maximum displacement, so the acceleration will be greater. Okay, so makin jauh kita tarik satu objek daripada equilibrium position, makin besar nilai pecutan. Okay, so means that makin besar nilai restoring force, where the restoring force direction towards equilibrium position. Okay, tadi kita dah tengok we do have an equation A equals to negative omega square y. Okay, we compare these two equation for spring and pendulum. Okay, we compare. So for spring, kita dapati the omega value, okay, sama dengan k over m. So we can write another equation, omega equals to sec k over m. So means that period akan jadi 2 pi sec m over k. Okay, sebab 2 pi datang daripada 2 pi bahagi omega kan. Okay, next for pendulum, kita compare pula, okay, omega square dengan G over L. So when we compare that, kita akan dapati the omega angular frequency is equal to sec G over L, which is period is 2 pi over omega. So means that the period for pendulum is equals to 2 pi sec L over G. So that's it guys. Thank you.